So now we're going to look at some relationships that exist between the binomial coefficients. The starting point for all these questions is the binomial theorem. I'd suggest you'd write that down every time. So if you put it in sum notation, 1 plus x to the power of n is equal to the sum of nck x to the power of k, going from k equals 0 to n. Sometimes it is useful to write the expansion out so you can find patterns easily. So nc0 plus nc1x plus nc2x squared and so on up to ncn x to the n. But again, I would include the general term somewhere in the middle of that expansion. So the first type of question where we have to find the values of some of these. So find the value of nck going from 1 to n. So let's say this first step, write out the binomial theorem. So 1 plus x to the power of n is equal to the sum of nck x to the k. And just have a look and see what's different between what you're being asked to find and what you've got. So we've got the sum. Well, the first thing I noticed there is it's the sum of 1 to n. We've got 0 to n. But also there's no mention of x. So what number could I substitute in to get rid of x? And really, there's only one number we can substitute in here, and that's x equals 1, because 1 to the power of anything will always be 1. So if we let x equals 1, now the binomial expression becomes 1 plus 1 to the power of n is equal to the sum of nck 1 to the power of k, which is 1. So 2 to the power of n is equal to the sum of nck, but we're going from 0 to n here. I want 1 to n. So what I do is I take out of the sum k equals 0. So substituting in k equals 0 into that nck, we get nc0. But there's my sum that I'm looking for, the sum from 1 to n of nck. So if I move the nc0 to the other side of my equation, I've got the result. I've just got to work out what it is. So 2 to the power of n minus nc0. Well, nc0 is always equal to 1. And so there's my expression. 2 to the power of n minus 1. Find the sum of all the odd ones. So nc1 plus nc3 plus nc5 and so on and so on. First step, write out the binomial theorem. But this is one where it's going to be useful to actually expand it out so I can have a look at what I want versus what I've got. So nc0 plus nc1x and so on and so on. Well, there's no mention of x. If I try that again, let x equals 1. So 1 plus 1 to the power of n is equal to nc0 plus nc1 and so on. Well, 1 plus 1, that's equal to 2. That in itself brings up an interesting relationship. What that's saying there is the sum of all the binomial coefficients on any row of Pascal's triangle will always be 2 to the power of n. That's a useful thing to remember. Now, I want to get rid of all of the even ones. So how can I do that? Well, if I substitute in -1 instead of +1, that means all the odd ones will become negative, because it'll be -1 to the power of n. So the even ones are positive, the odd ones are negative. So it will then alternate, plus minus, plus minus, plus minus, and so on. Now 1 minus 1, that is of course 0. I've got two equations there. I can now eliminate the odds or the evens, up to me which one I want. I want the odd ones, so I want to eliminate all the even ones. So in order to do that, I'd have to subtract the 2. So if I subtract 2 from 1, I get 2 to the power of n minus 0 on the left-hand side. So that's just 2 to the power of n. But then I'm left with 2 lots of nc1, 2 lots of nc3, 2 lots of nc5. Divide both sides by 2, and there we have it. All of the odd coefficients add up to be 2 to the power of n minus 1. Had the question asked for the even coefficients, I would have done exactly the same thing, except instead of subtracting, I would have added, and that would have eliminated the odd ones. K, N, C, K. Let's start with the binomial theorem, and let's compare what we got. Again, there's no mention of x, so we're probably going to do a substitution of x equals 1 in there. But how on earth do I get k in front of nck? So I've got to think of a mathematical operation that would bring the power to the front of the expression. And that's where I use calculus. If I differentiate both sides of my equation. So on the left-hand side, bring down the power, n, lower the power, n minus 1, diff the inside 1. And on the right-hand side, it's just a normal polynomial. So I'll get k, nck, x to the power of k minus 1. And that's now looking a little bit more like what we're trying to find. So let's say x equals 1. Let's make that x go away. So I get 1 plus 1 to the power of n minus 1. And on the right-hand side, 1 to the power of k minus 1. Well, that's always 1. We're close. Looking at the sum, we want 1 to n. I've got 0 to n. So if I extract k equals 0, and we'll get 0 times nc naught, well, that's just 0. On the left-hand side, you'll notice I've done the 1 plus 1 is equal to 2. But we now have our answer. The sum from 1 to n is n times 2 to the power of n minus 1. By equating the coefficients of x to the power of n on both sides of this identity. So let's have a look at that identity. 1 plus x to the power of n times 1 plus x to the power of n is congruent to 1 plus x to the power of 2n. Well, that's certainly true because we add the powers, and n plus n, that gives me 2n. We have to show this lovely expression here. Start with the binomial theorem. 1 plus x to the power of n is equal to the sum from 0 to n of nck x to the power of k. I think I'm going to expand it out this time. So nc0 plus nc1x all the way up to ncn x to the n. You'll notice I've added a few terms in the middle there. ncn minus 2 x to the n minus 2 and ncn minus 1 x to the power of n minus 1. Why have I done that? We see I'm going to be looking for the coefficient of x to the power of n. Because it's told me that by equating the coefficients of x to the power of n. On the left-hand side of our identity, we're multiplying 1 plus x to the n with 1 plus x to the n. So it's that expression I just wrote down times itself. We're looking for things that will produce x to the power of n. So nc0 in the first one would have to be multiplied by ncn in the second one. nc1 in the first one, and here's why I wrote these other terms out, would be multiplied by ncn minus 1 x to the n minus 1. nc2 would be multiplied by ncn minus 2. And we would keep going until we get to the end, and then the same thing would be happening. The ncn minus 2 would be multiplied by the nc2, and we work all our way down to the last one where ncn would be multiplied by nc0. But they would be all the terms that produce x to the power of n. Well, I'm not actually interested in the x's, so let's just look at the coefficients. So nc0 times ncn, nc1 times ncn minus 1, nc2 times ncn minus 2, all the way up to ncn nc0. Now I'm going to use the fact that Pascal's triangle is symmetric. So nck will equal ncn minus k, which means the first one, instead of being nc0 times ncn, I can rewrite as nc0 times nc0, nc0 squared. The second one I can rewrite as nc1 squared. The next one, nc2 squared, until I get to the very last term, and that will be ncn squared. If I put that into some notation, I've got nck squared. That's my general term. And I'm going from when k equals 0 to k equals n. Now that's the first half of what we need. Let's have a look at the coefficient of x to the power of n on the right-hand side of the identity they gave me. 1 plus x to the power of 2n. Well, that one's a little bit easier because 1 plus x to the power of 2n, I just apply the binomial theorem. 2nc0 plus 2nc1x plus 2nc2x squared. Somewhere in the middle there will be 2ncn x to the n, and it would keep going. But I'm only interested in the term with x to the power of n. And there's only one of those, and that's the 2ncn. So the coefficient of x to the n on the right-hand side is 2ncn. But hang on, those two things are identical. Therefore, the coefficients must be identical. And so we have almost our relationship. The sum of nck squared going from 0 to n is 2ncn. Not quite what they asked me to prove, because now I have to get the 2ncn and break it up in the factorial notation. So that would be 2n factorial. Now when you write something like 2n factorial, make sure you put the 2n in parentheses, because if you just wrote it without parentheses, it would look like you're saying 2 times n factorial. But that's not what we've got. We've got 2n, all of that, factorial. At the bottom of the fraction would be n factorial. Well, that's the same as saying n factorial squared, and that's the result they were looking for. Now, this brings me to last year's Extension 1 paper, the very first paper in this new course. And a lot of people got upset with this question because they thought in this new course that these identity questions that we've just been looking at, well, they're not in the course, but they are. And this is where the 2020 question basically used what we have just done. You'll see that the very first part of the question is the same as what we just did. So I'm not going to redo it because it's essentially the same as the last example. So we have now proven that 2ncn is equal to all of those squared. Part B, it turned into what looks like a permutations and combinations question. A club has 2n members, n women and n men. Now, a group consisting of an even number of members. So it either has 0 members, well, I don't know if you can call that a group, but okay, 2, 4, 6, 8, all the way up to 2 times n, if everyone is in the group. But basically what they're saying here is there's got to be an equal number of men and women in the group. So show giving reasons that the number of ways to do this is 2ncn. Okay, let's break this problem down. First of all, I'm going to choose the men. So I'm going to choose k men from a group of n. nck. The order's not important. I'm just choosing the group. So nck. Now I'm going to choose the women, but that would be exactly the same because we have to have the same number of men as women. So if I just chose k men, I now choose k women, and that would also be nck. So the total number of ways of choosing both k men and k women would be nck times nck, nck squared. So that was generalising it for k. So the total ways of choosing the same number from both groups then, I'd have to give all the possibilities for k. So k equals 0, if that is a group, but k equals 0, 1, 2, all the way up to n. Sum notation, nck squared of 0 to n. And that is what we just said in the first part of the question is 2ncn. So the next part of the question said, from the group chosen in part B, one of the men and one of the women are selected as leaders. So there are 2 leaders, one male, one female. Show, giving reasons, the number of ways to choose the even number of people, and then the leaders is this expression here. So basically we've got to explain why. All right, so how many ways are there of choosing the leaders? Well, choosing the groups, we just said, was nck squared. That's if I'm choosing k men and k women. So nck squared. So I've got my group of k men and k women. I'm now going to choose the male leader. I've got k to choose from. So I've basically just got k choices. So times k. Now I'm going to choose the female leader. Once again, I've got k to choose from. So times another k. That was just for the generalisation of k. Well, I think I've pretty much decided now that k equals 0 is not a group here, because if I'm not choosing any, how do I pick a leader? I can't. So in our sum, we must start from 1. So k equals 1 to n, my general term that we just worked out, k squared nck squared, which would be, if I write that out, 1 squared nc1 squared plus 2 squared nc2 squared, and so on. Now, I suppose if you didn't think about the k equals not being a possibility, it wouldn't matter, because in your general term you would have written 0 squared times nc0 squared, and 0 squared is 0, so it would go away anyway. Question didn't finish there. Part D, we're basically reversing the process. So the process is now reversed so that the leaders are chosen first. Then they go pick the rest of the group. But still same rules. You've got to have the same number of women as you do men. They've given us a hint by considering this reversed process and using what you just did before in part B, find an expression. Well, if we choose the leaders first, I'm always going to have n possibilities for the male leader and n possibilities for the female leader. Then, to complete the group, well, remember we're choosing groups of k. I'm talking about the general possibility here. So I want to choose k men all up. I've already picked one because I've picked the leader. So I now have to choose k minus 1 men, but there now are only n minus 1 to choose from because we picked the leader. So k minus 1 from n minus 1. So in other words, n minus 1 see k minus 1 ways. Now the same thing would happen to the women because the numbers are identical. So the total number of ways, my general term would be, I'm going to pick the male leader. There was n ways of doing that. Times, I'm going to pick the female leader. There's n ways of doing that. N times n, n squared. Then I'm going to pick the rest of the men, n minus 1 see k minus 1. Now I'm going to pick the rest of the women. That's also n minus 1 see k minus 1. So my general term becomes n squared, n minus 1 see k minus 1 squared, and we're going from k equals 1 to n. So let's expand that out, and I'm going to be left with n squared, n minus 1 c naught squared, plus n squared, n minus 1 c1 squared, and so on and so on and so on. I can pull out the n squared, so I'll have n squared outside of n minus 1 c naught squared, plus n minus 1 c1 squared, plus and so on and so on. But we can use our result. It's just that instead of the sum of nc naught squared, so now using our relationship that we proved back in part, I think it was part B, that sum I can rewrite as 2n minus 1 cn minus 1. Basically, I've replaced the n with n minus 1, which is the same as 2n minus 2 cn minus 1. And there's the relationship they're looking for. Very tricky question that they put in last year's HSC. Caught a lot of people out. 15D. Play around with some of these relationships. Let's see what we can prove and what we can show.